Hi, welcome back to AP Physics 1, Unit 2. Again, we're still working through dynamics. Um, this is topic 2.8, I think, or 2.7, which means we have 2 more videos to go here in this unit. And in this video, we're going to talk about spring forces. So what happens when we have springs now, having forces exerted on them to cause them to stretch or compress? So the first thing is that we're always going to assume that these springs are ideal, which means you don't have to worry about their mass, and that the amount of force that gets exerted on it is proportional to how far it stretches. Okay, when you see this term relaxed length, that we can just think of equilibrium. Okay, that's where it wants to be. All right, and so something to note is that this force that we're about to talk about wants to bring it back to that point. So the magnitude of the force that we talk about with springs is something called Hooke's law. So Hooke's law says F sub SP equals negative K delta X. Okay, and some things about this equation. This negative sign just means that it is a restoring force. Okay, as mentioned, it wants to bring it back to its initial position, right? So it wants to restore back to that initial piece. And then this K value, all right, is something called the spring or force constant. So every spring has this value. It just says how hard or easy it is to stretch or compress the spring. So something like a slinky. A slinky has a very low spring force, spring constant. So it's a low K value because if you take it, like you can literally, well, I just happen to have a slinky at my desk. So I can easily do like this and stretch it far without exerting a lot. On the other hand, garage door springs, okay, they have high K values because it's very hard to stretch those. I mean, you have to use like a 1.5 horsepower motor to even stretch them just a little bit to open up that garage door. Okay. And then delta X is just your stretching or compressing. Okay. Sometimes they call it the, I forget. Sometimes well, just to understand. Oh, elongation is the term I'm thinking of, right? So sometimes they think they call it the elongation. Okay. Now, again, like we always says, the force is always going to be pointed to the equilibrium position. So if, let's say, the equilibrium position on this one is here, that force is going to be pointed in that direction, right? So it's going to be pointed towards the equilibrium. Same thing here. If this was the equilibrium position, the force will always be pointed back to it. Okay. So that will allow us to find, the acceleration at these points. It'll help us find, how much force was, or what was the mass that we put onto it. Okay. And so the object spring system, right, or should say probably mass spring system. So the mass spring system can either be horizontal or vertical. And one of the common things that they'll ask you to do is find the acceleration. So if I'm drawing a free body diagram, right? So I have my applied force, and then you have your spring force. In fact, if we release it, we don't have the applied force anymore. So we can just get rid of that portion, right? And so we just say, there's our draw, right? Then we got the sum. So we say net force equals MA. Well, the only force acting on it is F delta X. Okay. And then just solve this for A. Divide both sides by M. And you'll find that the acceleration of a spring is F delta X divided by M. And this works for both horizontal or vertical. Okay. Now, sometimes with the vertical, it may be a little confusing that there is the extra force of gravity in there, but through the algebra, it shows up that the acceleration will always equal this negative F delta X, or not F, K. Sorry, I apologize. That should be a K. It's like, where'd the F come from? We don't know what that is, right? So these should be, sorry about that, negative K delta X over M. All right, so let's look at an example problem involving these spring forces. So here we have a spring. It's on a surface. The spring constant is 95.5 newtons per meter. The block is moving rightwards, and the spring's right is displaced from 0.20 meters to 0.220 meters where it's held in place. All positions are measured from the wall, or from the origin, which is the wall. What is the spring force exerted on the block? Now, if the block has a mass of 10 kilograms, what would be the acceleration of the block if 0.220 mils is the place where it's stretched to let go? Okay, so what we need to do first, sorry, I was misreading that. I thought it said spring constant, but we already have that. So we just say FSP equals negative K delta X. It tells us a K of 95.5. And note the unit, right? The unit for K is newtons per meter. So that's how much force you have to stretch it to go essentially 1 meter. So for this spring, we'd have to apply 95.5 meters or newtons to stretch it to 1 meter. Okay, and then we just do our delta X. Note that we're not stretching from 0, so we have to account for that. Right, so the 0.220 minus 0.200. Plug it into our calculator, and we find that the force is 1.91 newtons. Okay, so that is the first question. What is the spring force exerted on the block? Now, the second part says, what is the acceleration of the block if we let it go at 0.220? Okay, so we just derived the acceleration equation, right? Negative K delta X over M. Well, that negative K delta X is actually the 1.91 meters we just had, okay? And we're hanging there's a 10 kilogram block attached to it. In fact, I forgot the negatives. The negatives, they may say magnitude of the spring force or the magnitude of the acceleration. So it's not a big deal that we didn't write it in originally. So we're going to do negative 0.191 divided by 10. And that's going to give us an acceleration of negative 0.191 meters per second squared. Okay. Now, if they ask you to go right to acceleration, then you may have to do your derivation, right, where you have to derive the equation for acceleration by using Newton's laws. But we already had it. We already have the spring force, so that all we have to do is just plug it into our acceleration equation that we derived on the slide. And there it is. So that is spring forces, which just leaves us one video left with circular motion.